Hello class, this is Andrew Furlow representing Group A, which consisted of Joel, Brandon, myself, Jason, and Michael. And for our course project, we did a critical review of the paper, A Model for Hyperelastic Materials Reinforced with Fibers, Resistance to Extension and Flexure. The core concept of this paper was a J-shaped stress-strain response, which is different than the linear response between stress and strain that we typically see in our graduate engineering courses. This type of response is typical for biomaterials. At low stress levels, strain increases rapidly, and then at higher stress levels, strain slows down and deformation is much harder to achieve for consistently increasing stress. And this is classic for biomaterials because under normal stresses, they need to be able to deform, but under higher loads, they need to resist deformation to prevent failure, which would result in the breakdown of the body. An example of an engineering application of this type of response is a biomedical stent. This is a mesh-shaped object that is placed inside of a blood vessel in order to keep it open. So under normal stresses, which would be the typical stresses within the body, the stent needs to be able to flex and contract with the blood vessel itself. But when vessels are subjected to external compression, the stent must resist that deformation in order to keep the vessel open, thus leading to the J-shaped response. So in this paper, the researchers attempted to derive a model for this type of response, specifically for elastomeric composites, which are elastomeric materials that are reinforced with a type of polyester fiber. And in order to drive this model, the researchers used a continuum-based model, which is the same type of theory that we've been using in ME551. Once the model was developed, the researchers were able to verify the J-shaped stress-strain response and strain stiffening phenomenon, and then they compared it to given models within the literature that currently exist, as well as experimental lab data. And lastly, their findings were able to be extended to certain design applications. This is a list of some other research that was referenced in the paper. Specifically, I think it's important to note that other researchers are determining this type of response by analyzing the elastomeric material and the fibers separately and then combining, which is different than the continuum-based model that's being used here. So to begin deriving this model, the researchers made several assumptions, including unidirectional composites and fibers, finite and elastic deformations, straight fibers before deformation occurs, aka initial conditions, no out-of-plane deformations, and constant material properties in the out-of-plane coordinates. So essentially, from the model at the bottom, you can see that the applied stresses were unidirectional or axial, and the overall composite is comprised of a bulk elastomeric material and integrated fibers. To derive the model itself, the researchers followed the given methodology, which was to define the orientation of the fibers, express the deformation of the fibers, and therefore derive out of that strain energy. So mathematically, the researchers defined a parametric curve that represents how the fibers were deforming, as well as the unit tangent along that curve. And then similarly, for the undeformed state, they defined x and s. Then, under deformation, the researchers defined the extension of the fibers with a chi function, and they also utilized the first and second gradients of that deformation, which is a procedure that had been used in other research. So with all of that, the researchers were able to derive the curvature of the fibers as the function g, which is the second derivative of the parametric curve, which, as we know, curvature is the second derivative of a curve. Moving forward, the researchers were able to back out a strain energy representation, which is given here, which is a function of deformation, extension, and curvature of the fibers. Strain energy itself was then found by integrating the strain energy variation and then minimized in order to determine equilibrium conditions. So that would be the derivative of the strain energy. By conducting that integration, the researchers were able to derive the expression PIA, which is known as Paola stress, and that's essentially a formula to represent the stresses that are being applied axially to this elastomeric composite. Then, based on this, the researchers used an Euler equation, which was given from other research and assumed to be proven already. And also from that Paola stress, the researchers were able to derive these expressions for boundary conditions, which are also similar to what we've done in our class, just obviously a lot more complex for a fiber composite. Then moving forward, that model was reduced using the Mooney-Rivlin strain energy potential method, which allowed the researchers to use that representation of strain energy and derive it in terms of stress invariance. Again, a reference back to what we've done in ME551. So using those two methods, along with the Euler equation and the boundary conditions, the researchers were able to back out a complete partial differential equation system, which could then be numerically solved using standard software, which I'm sure many of you have done in other courses. So down at the bottom here, you can see an example of a set of PDEs for a given set of boundary conditions. These PDEs can be varied for various conditions and materials, so this was just an example that was given in the paper. Once that model was derived, the researchers were able to plot a stress-strain response and verify the J-shaped behavior. And then they were also able to compare it to the given Holtz-Opfel model from other research that they referenced. And lastly, both those models could then be compared to a real-life material known as EcoFlex 0050 that was reinforced with various types of fibers, both polyester spandex and nylon spandex. Here in the image below, you can see the laboratory test that was conducted. Between the two large metal blocks is the actual elastomeric composite material that was stressed uniaxially in order to derive a realistic model of the response. So for the first materials, the polyester spandex, you can see here that the proposed model that they derived definitely matches the laboratory experimental data. And the Holtz-Opfel model also matches, but in the lower strain regions, you can see that the proposed model was actually much closer to the real-life data, which is important because many biomaterials actually function in this low strain mode. So having a more accurate model would allow for design of more accurate materials in that strain regime. Again, for the polyester spandex fibers, the J-shaped response was confirmed, and it was also seen that the proposed model was more accurate than the Holtz-Opfel model when compared to experimental data. Based on the stress-strain response, the experimenters were able to back out a mathematical definition of deformation, which was then compared to the laboratory deformation that was seen from stretching that material shown before. So from the curves, you can see that the proposed model is quite close and accurately represents the deformation. And on the right here, you can actually see the physical material itself after it's been deformed, and then compare that to the computer-generated model, and it's visually extremely close. It's definitely a very accurate representation. For a different material, the nylon polyester material, it was actually shown that the deformation could not be accurately predicted, which would be the chi-2 direction on the right. The researchers propose that this may be due to the unidirectional fiber assumption that was made in the beginning, and that a bidirectional model may be better suited at finding this deformation. And the reason for that was because fibers with high bending resistance tend to resist deformation in the chi-2 direction, which was not accounted for in that assumption. Lastly, along with the stress strain and deformation, the researchers were able to derive a model for shear strain angle. So again, here in the image, you can see the actual physical material that's been deformed, and then using MATLAB image comprehension software, the image was able to be colored depending on the various angles that were calculated. And again, comparing to computer simulated shear strain angles, you can see that the layout of the angles and how they were predicted is quite good. So to summarize, the researchers were able to derive stress, strain, deformation, and strain angle, which are definitely important parameters when it comes to design. So as I mentioned, in the low stress region and low strain region, their model was even more accurate than currently accepted models, which for biologic materials such as tissues, arteries, muscles, tendons, ligaments, that is the region where those tissues are stressed. So this model can be used in determining the outcome of those tissues or engineered replacements of those tissues. Next, this model was continuum based. So material properties were built into the material, which is different than other models that have been derived. In other research that's been done, the researchers needed to actually fabricate a material and then test it to determine if the model response was accurate. But for this model, because it is continuum based, material properties could be picked beforehand, and a material could actually be designed to fulfill those properties for a desired output, such as stress, strain, deformation, what have you. Next, deformations and shear strains were accurately predicted. So for highly strained materials, this model would be appropriate for predicting the material failure, because we know under large deformations or large strains, a material will fail, and this model could be used to predict such a failure based on material properties. And fourth, as I mentioned, the model was limited for certain materials based on bending, rigidity. So further research should be done to derive a bidirectional fiber model, because that may be more accurate at representing such a material. And that's it for our presentation. I hope you guys enjoyed, and feel free to reach out if you had any questions about our paper. Thanks.